Ba-ba-ba. Recording in progress. That's always helpful. All right. Didn't like me sharing just the application. Got very upset. So, hello everybody, and welcome to the workshop. I'm glad you're all here. And thank you, Andris, for the wonderful introduction. So we'll be doing quantum circuit design and execution. And if you haven't ever used real quantum hardware before, you'll be able to leave this session saying that you have. You've actually developed a quantum algorithm and executed it on real quantum hardware. And I think that is the coolest thing to say. All right, so well, you already introduced me, right? PhD in physics from University of Florida. Go Gators! I think I'm contractually obliged to say Go Gators every time I say UF. Have a PhD in physics from University of Rochester, master's in technical entrepreneurship management, and doing marketing at Classiq. So doing everything I ever wanted to do with my physics degree, which is talk to cool people about physics. In today's workshop, we'll go over a little bit of what is the Classiq platform, or sort of a little bit of introduction, right? What is the Classiq platform? And then we'll get right into the hands-on workshop, right? We'll go through a couple of things. We're probably not going to go through all of these steps due to time, but we'll see what we can get through today. So Classiq, we're a quantum software development company where we developed a platform for designing quantum algorithms all the way from well, design to execution. We just finished our Series B funding round about halfway through last year with about 63 million. We have actually probably well over 70 employees at our company now, because about every week I join these weekly company meetings and there's 1 to 2 new employees every week. So we're well above 70 since the last time I made this presentation. Companies based in Israel, but we also have offices in the US, in Europe, and we're opening one in Tokyo, Japan pretty soon. And we work with both Fortune 500 companies and universities and researchers. So why I'm here today in general is that the Classiq platform has an academic program that we launched with Microsoft. So the platform is free for essentially anybody with an @edu email address. So if you have an @edu email address, you get both the Classiq platform for free to use for research purposes, for academic purposes, for coding competitions. But you also have access to all of Microsoft Azure's quantum hardware for free as well. And that means anything from their quantum simulators to their 80-qubit Rigetti quantum computers. And professors are certainly liking this one because they don't have to use their grant funds for doing their research on quantum computers. And it's really fun to be able to program on quantum computers beyond kind of the usually free 5-qubit systems. To be able to program on an 80-qubit quantum computer is pretty cool. So the Classiq platform at large lets you interactively design, analyze, and execute optimized quantum algorithms using high-level coding. So when we're talking about this high-level coding, you know what? Here's a good step. Who here has programmed using Qiskit before? All right, good show of hands. Anybody else? We got 2. Oh, 3. 4. Oh, fair. I guess I can broaden it up. Qiskit, Penny Lane, any of the basic ones, right? For learning quantum computing. Okay, cool. So about a 50-50 split here. Now, so then you're used to programming things kind of on the right side here, right? In the assembly level language, C gates, C0 gates, Hadamard gates, and so forth. That can get quite tedious once you start expanding past 10 qubits, right? Doing this for 2 qubits is fine. Doing this for 5 qubits is fine. 10 qubits starts to get a little bit complicated, right? I've certainly missed C0 gates here and there when I start going from 10 and beyond. But with the Classiq platform, instead of doing things at the assembly level language, we're programming things using higher level functions, right? We're calling things out like state preparations. We're calling things out like adders or like Grover's algorithms. Instead of doing things at this assembly level language, you tell the system what you want to do instead of having to work essentially in the Boolean logic level of classical computers. And what this means is that it's highly scalable, right? It's going to take you everywhere from, learning how to program on 5 qubits to expanding that out and doing, 50 qubit quantum circuits all the way to 1,000 plus qubit circuits. And right, how do we do this, right? Because certainly it's going to soon be very impossible to design, debug, or maintain quantum algorithms as quantum computers start getting larger, right? IBM just came out with their Condor machine, I think it's called, with 1,000-something qubits on it. That's not something I want to do using assembly level language. That'd be quite a bit of a challenge. So how have we solved this? Well, this kind of a problem hasn't, we've seen it before. About 60 years ago, we faced this with classical computing. There was essentially the electronic design challenge. We started to get to a place with circuits that it started becoming untenable to do designing your chips and circuit, transistor by transistor. We used to be putting them, by hand, specifically saying this transistor goes here, this transistor goes there. But as we started to get to what now there's millions of transistors on a chip, that's impossible to do, but by hand. So the way we solved this was to develop electronic design automation. So automated methods where you model out the functionality you want on that circuit, and then the transistor layout gets modeled for you depending on what you wanted it to achieve. So how's this relate to quantum computing? Well, at Classiq, we've developed quantum algorithm design automation. And what that means for end users is that you have intuitive programming and automated circuit synthesis. So you don't have to do, right, like I just said, designing things at this Hadamard gate, CNOT gate level. By defining things at this higher level, you model out what you want your quantum circuit to do. And then the quantum algorithm design automation, it goes ahead and it implements and finds the quantum circuit implementation that meets your model and your constraints. This isn't a trivial thing to say, right? So this is beyond even kind of what you would consider a compiler kind of system, because it will make decisions for you. It'll make like the system level decisions for you, right? What algorithm implementation should I choose? Should I choose a QFT adder? Should I choose a ripple carry adder for the use case I'm trying to use? Which is the best way to go ahead and reuse auxiliary qubits? Should I use one function versus another because it uses more or less of these? And there's trade-offs with all of these, right? There's block level considerations like, how many auxiliary qubits, right? What's the level of accuracy do I want this algorithm to have? But then there's system constraints, right? What's the circuit connectivity map for this quantum computer? What's the native gate set for this quantum computer? And choosing the right quantum algorithms for all of these parameters and optimizing for one of these, right, isn't trivial. If you want to optimize for depth, you're going to increase your width. If you optimize for width, you increase your depth. If you want to minimize the number of CNOT gates, what's that going to do to your quantum circuit? And how do you play with those trade-offs? So here's a fun one. Can anybody tell me what this quantum circuit does? I will pause for an awkwardly long amount of time. Any guesses? No takers. Okay. One more. Does anybody know what this circuit does?
This is probably wrong. Does it add 2 bits?
It is an adder. Yes, they're both adders.
Okay.
They're both different ways to do addition, right? And this does a couple of things, right? It shows that it's not simple to understand quantum circuits when you see it at this gate level. And also, there's more than one way to accomplish the same exact functionality. You get the same solution at the end of the day, but there's multiple paths to get there, and choosing which one isn't always the easiest. All right, so can anybody tell me what this quantum circuit does? This is all one quantum circuit, kind of going from the top left here, going to the right. All right, let's try this. Let's raise it up a level. You can see that by essentially abstracting out your quantum algorithm, you can easily see that, hey, this is a Grover operator, right? This is two-state preparations going into a Grover operator. This is Grover's algorithm, right? Again, seeing things at the assembly level language, it's really hard to understand what your quantum circuit does. And certainly what happens to me when I program at the assembly level language, if I program a quantum circuit and I don't look at it for a week, I'll come back to it. I have no idea what I just programmed. I'd almost have to start over again to figure out what I'm doing. I should get better at commenting my programs, but I'm terrible at that. It's unintuitive and you lose the intent of the quantum circuit. So, right, not only is it important to program at a higher level language, it's also important to visualize your quantum algorithms at this higher level. Actually, here's just a, let's see. Oh no. Yeah, it's supposed to be a video, but we'll see this all interactively together with the Classiq visualizer. You can go ahead and interactively navigate your quantum circuit. You can expand them out, contract them out, and see everything you want to see in your quantum algorithm, all the way from high level to the base unitary gate operations. So here's a quick example, essentially, of what we're doing today programming quantum computers. You have to define what you want your functionality to be for your quantum algorithm. You have to find some pre-existing algorithm that meets that need. You have to modify that for your specific use case. You optimize that, and that last little bit is the compilation transpilation step when it hits the hardware. It'll do a couple of swaps and cancellations for you. It'll translate your quantum algorithm to the native gate set if it's not already, or put in gate swap operations if the qubits in your circuit don't communicate in the way the actual qubits communicate, right? If you program quantum one, qubit one to talk to qubit two, but the hardware doesn't actually connect that way, it's going to have to do some swap gates and expand out your quantum circuit, actually making it unoptimized. So what we're doing at Classiq is automating most of the process. You still have to define what you want that functionality to be, but the system is going to go ahead and look at the pre-existing algorithms. It's going to modify that, optimize it, and give you that quantum circuit that both meets your functionality and lives within the constraints you want it to. And we actually did some benchmarking around this. We wanted to see how this compared to other quantum algorithm platforms. And so we chose Qiskit because that's kind of the tried and true. If most people start off in quantum, they're starting off using Qiskit. So we wanted to see how does it compare. We had a fun example was doing the ansatz for H2O, and you could see quite nicely that the savings in circuit depth are quite large when you're looking at Classiq versus Qiskit, both in the circuit depth, but also the number of multi-qubit gates, C-NOT gates. We looked at controlled adder circuits. We looked at multi-controlled NOT gates. And consistently, we're showing that the Classiq platform is able to better optimize your quantum algorithm for your specific use case. And a lot of times, up to 97% shorter quantum circuits compared to kind of these cookie cutter implementations. Penny Lane, Qiskit, these algorithm platforms are excellent tools for learning quantum computing, seeing how the block sphere shifts. But when you want to be doing quantum circuits that take, 20, 30, 50, 100, qubits, you need something that can optimize so you can fit the quantum program you want on the quantum hardware that exists today. And essentially, you also want to optimize as short a depth as possible because we're living in this NISQ era, right? This noisy intermediate quantum era. And the longer your circuit depth is, the noisier your quantum output, right? Your solution is going to be because qubits right now are quite lossy. And the longer a computation takes, the more noise is implemented in your system. So it's behooves you to try and optimize it as much as possible to get as true a solution as possible. So Classiq, like I said, it's not just the higher level modeling and automatic synthesis. We also have analysis and execution in the platform as well. You could do things like see what the qubit resource distribution is, how many single or multi-qubit operations are happening per qubit, what's the circuit connectivity map for the algorithm you just developed, or you could see how your quantum algorithm would map onto the hardware you want to run on. And we also have a hardware comparison table where you can see what your quantum circuit would look like if it was transpiled down to all these various hardwares from, IBM's, Amazon, Microsoft's. You could see what would that look like. What's that circuit depth? And once you're done analyzing it and reviewing it and seeing, which quantum hardware would be most optimal for your circuit to run on, we have flexible execution. So we're play quite friendly with most of the quantum hardware vendors. So if it's on the cloud, chances are we have access to it and you can go ahead and execute on it. So we work with AWS, Microsoft Azure, IBM, right? We have NVIDIA simulators, we have IonQ on our system. And here's just a quick snapshot of what it looks like to execute and see some solutions in the Classiq platform. So, and the fun bit is when you execute quantum circuits with Classiq, right? So here's a quick view of it. It's as simple as picking the hardware or simulator you want to run on. You select the number of runs and you hit run, right? It's not difficult. We try and make it as simple as possible to both generate your quantum circuits, but then to also execute them. You don't have to worry too much about how do I hook up to the hardware? How do I connect to it? What parameters do I need? When you're running a quantum circuit, for the most part, you just need to say, what's the hardware? How many shots? Click, run, go. In certain situations like Grover's operations or some financial calculations where you might need amplitude amplification or estimation, we also have that in the system, and it's a simple toggle that you just go ahead and click. And we'll see all that interactively when we join in on the hands-on portion. It's going to happen in a second. But just wrapping up, right? Classiq, like I said, it lets you interactively design, analyze, and execute your quantum circuits all in one platform using a higher level modeling language. So, right, we start off with modeling, system gets automatically synthesized your circuit. You can go ahead and visualize it, and then you can execute however and wherever you want. So let's go with the workshop now. So that was enough preamble for this. Let's have some fun, right? So there's a couple of implementations for the Classiq platform. We have both the IDE, so an integrated development environment, browser-based, and we also have a Python deployment. And you can use that on Visual Studio. You can use Jupyter Notebooks, however you like to play with Python. But the way to start off with the Classiq platform and to get onboarded is you go to this website, platform.classiq.io, and I encourage everybody here to go ahead and navigate to that and to create an account. So you would go to this button, onboarding, and go through that process. You put in your @edu email address, and you'll get access. So once you're there, I'll just keep talking for a little bit while people start navigating to that website and interacting, and hopefully you'll get an email quite promptly saying, here's your, click authentication kind of thing. We have tutorials in that homepage as well. We have basic and advanced. So the basic tutorials will take you through state preparations, some maths, and as well as Grover's search. We also have advanced tutorials that'll take you through other optimization algorithms, HHL, which is very fun. And we're actually working with quite a few clients on HHL algorithms. We recently announced we're working with Rolls-Royce on their avionics division doing computational fluid dynamics using HHL. Actually, we just recently announced, I think like a week ago, that we're also working with NVIDIA on that. So us, NVIDIA, and Rolls-Royce are working together on this project, and it's really cool. We also could do, Monte Carlo simulations. You can see it in the advanced tutorial. Super cool application, right? Because it's one of those applications for quantum computing that shows definitively quantum Monte Carlo, the confidence interval scales faster than the classical version of it. And as soon as you say that to anybody in finance that you have a better Monte Carlo simulation, they want it. Because Monte Carlo simulations is pretty much in every financial calculation you deal with. We also have a Slack community. So you can go ahead on the bottom here, click that, and join our Slack. You can talk to other community members as well as our developers and ask them questions if you're using the platform. And we also have a pretty robust user guide where you can go into there and really dive into all of the pre-existing algorithms we have in the system, see how you can develop and implement your own custom algorithms in the platform to be optimized around as well. We have a lot of fun functionality that you can mess around with and have fun with, especially with analysis of your quantum circuits and optimization, different parameters you can pull. So like I said, right, the onboarding, you click on that button, you go through the academic registration, and you should be all set. Let's see here. Any questions?
So sorry, I'm interested signing up for this. Is it just the schedule a demo page, or did I miss where we need to go to input our information?
So let's go to the page, platform.classiq.io.
Fantastic, thanks.
Yeah, if you go to classiq.io, you'll get to our main homepage, and you can click on the academia section and navigate through there. But I find it easier just to tell everyone, go straight into the platform. So I'll wait a little bit, but then afterwards, it's your turn, and we'll start doing a full end-to-end quantum experience.
Hi.
Yeah.
So I'm trying to do the onboarding, and then I say, please sign up with my academic email. And then I click the sign up, and then it just takes me to the next page and says verify your account. And I don't actually see an email in my academic email because it didn't ask for me to put in my email.
Interesting.
It worked fine for me. I'm not sure. Did you go to the platform, the same address you put up?
It didn't prompt me to put in an email address. It just took me right to the next page.
Interesting. Let's go together.
I went through the sign up with Google and then use the edu email that way. That worked.
Oh yeah, I'm already authenticating the system, so it's angry at me. Let me log out.
I reloaded the page and it's letting me now. So
excellent. Good.
Thank you.
All right. Anybody else having any onboarding issues, or feel free to let me know. Sign up. I'm already signed up, so I just log in. Oh, sign up. Sign in Google. Okay, good. Every once in a while, it makes me use my authenticator app. Okay. No, it's so cool to see the things these developers have put together so quickly. I feel like every month the developers come out with something very cool and new. And this was put together, I think, in the last 2 months, and it's pretty cool. The browser-based version of it used to be only Python. So I love that you could just do everything within a browser. So, a lot of times some users have some issues downloading Python and things like this, and maybe it's the wrong Python version or whatnot. Hopefully we don't run into any of that today, because later in the workshop we'll be going to the Python files, but I want to start everyone off using this browser-based version. So let's go back to the PowerPoint. All right. So let's see a quick raise of hands for anybody who still needs time. All right, looking good. Okay, cool. So let's start off by going to that synthesis page. It should be that first tab. I want you all to go and generate a model of the default state preparation. So you click on state preparation. It should be one of the example files you can load up from the top. Press synthesize. I'll navigate to that with you, everybody. So we're all together. I'm going to go synthesis. I already had it loaded up, but you can go and click on state preparation here and click synthesize. So you can take a look at what all this is on the side, but it's loading in a linearly increasing probability mass function. I'll walk through what this is. So we're calling the function state preparation. We have our probabilities. Here's my ChatGPT thing keeps getting in the way. We're loading in all of our probabilities. And then we have an error metric saying, how closely do you want the quantum algorithm that's going to be developed to match these probabilities? The closer you want your probabilities loaded into the computer to be true to these numbers, the longer your circuit depth is going to be. If you're okay with a little more error and a little more variation in your kind of histogram bars at the end of the day, you could have a much shorter circuit. But that's a trade-off you have to consider when you're loading in your data. And like any kind of physics question you deal with, how accurate do you need your solution to be? Are you okay with round cows? Or do you need a little bit more detail in what you're dealing with? So you have to put in how detailed and how accurate do you need those initial states to be when you're doing your quantum calculation. Do you have a question, Ben?
Yeah, I do have a question. So this error metric, this is Kullback-Leibler, so it's like the divergence. So is this for the initial state? Why is it about why is the error metric related to the probability, the like Born amplitudes and not the complex amplitudes themselves?
Yeah, so again, right, it's kind of how you deal with the block spheres, right? There's only so many native operations on a quantum computer. So to rotate the block sphere to be at the exact location you need it to be requires more and more and more permutations, right? So the more accurate you want it, the more gates you're just going to need to get exactly there, is what we're trying to say. And right, we're doing KL here, but you can do L2, loss of fidelity. We have different ways to measure or specify your error metric. We try and replicate really as closely as possible to academic papers. So if you see an error metric labeled in an academic paper, chances are you could implement it in the Classiq platform. And every paper has a different way of doing their maths and their calculations. So we tried to implement as many different varieties as possible. And then we're saying, yep, we need 8 qubits for this. We have the max depth of 5, max width of 5 qubits, max depth of 1,000. And that's specified up here. And you can go ahead and toggle these. But like I said, let's go ahead and synthesize this. Get our output. So it looks like the depth is 363 using 5 qubits, 204 single rotation gates, 192 C0 gates. And you could expand this out and see how it got implemented. You can go ahead and even expand it out all the way to the unitary gates and see all of the minutiae of it, or collapse it all. And you can do some fun things like even download an interactive HTML file so you can keep for yourself later outside the platform. A lot of professors do this for their classrooms. They'll save some quantum algorithms to show and demonstrate with the class. You can download the CHASM file if you want to see all the raw code for this, or just take a quick photo. Or JSON if you want to plug it into your Python. Let's go back to that PowerPoint. All right, so we viewed the circuit. We can go ahead and change that circuit's name instead of that very long, raw, code we got there. And after that, we're going to go into the execution page and execute on either IonQ simulator or the IBM AER simulator. And those are just 2 of the simulators you can use without having to type in any kind of API keys. The IBM AER simulator, you don't need it because since that's actually a public simulator, we have a version of it in our platform implemented just for some quick iterations of quantum circuits. And the IonQ simulator is free and doesn't need an API key because we're partnered with Microsoft, and any of their resources you can use for free. So let's go back to that. Yeah, let's rename this, because that's an ugly name. But 2023-531 T15 demo. I'm not feeling original, so I'm calling it demo. All right. So when you are done renaming that, you can go to execution. You click the circuit you want to run, in this case, demo. And that's why it's useful to name them, because you can see all of my terribly named circuits beforehand. It'd be very hard to distinguish these. You click the vendor you want to run on. In this case, I'm going to do Azure. So I'm going to click on Azure Quantum. I want a simulator in this case, and let's do the IonQ simulator. Let's open it up. Looks like it has a queue time of 3 seconds, so not many people are using it right now, which is perfect. It can have a maximum of 29 qubits. Excellent. 1,000 shots seems lovely. We can give it a job name. I'll call it demo run, just so I can separate that out from the other executions I have. And I'm going to click run. All right, so it's all queued up. 3 seconds is pretty fast, so it's going to return to us some results in just a moment here. Excellent. Okay, so we see here our linearly increasing probability mass function. And there's a little bit of deviation. So if you needed it to match more closely to your probabilities, you would have to tighten up that tolerancing parameter. So you'd end up with a much longer circuit, but you'd end up with a more accurate probability mass function. All right. Did everybody follow along to this step so far? All right. The 2 people on camera I can see nodding, so good. Well, Andris is on camera, but you're not nodding. Very stoic. All right, cool. So let's go back to the PowerPoint. Excellent. All right. Oh, cool feature break. Yeah, you can rename any of the quantum blocks also. So on top of renaming the file itself, you can go into any of the functional blocks and rename that as well. And that's a lot of times what professors are doing in classrooms too. They'll name them specific things or add details in there. So it's pretty cool, the customization you can have in the system. You can even go ahead and color the different wires. If you need to specifically track certain qubits, maybe you want to track an auxiliary qubit for any reason, you can go ahead and color your different wires as well and name the qubits. All right, so let's go into developing, our first IDE-based quantum algorithm. So we just ran kind of the default one that was there, but this time let's go back to that state preparation example. Let's load it up again. And instead of the default probabilities given to you, let's go ahead and load in these probabilities. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 states. Can anybody tell me how many qubits that's going to take?
3.
You got it, right? 2 to the 3rd power. Perfect. So we got, we need our 3 qubits. So when you get to that parameter, you make it 3. And instead of that, that K2, we want to use loss of fidelity in this case. And let's choose an upper bound to be 0.01. And we're going to go ahead and run 2 of these circuits, one with 0.01 and one with 0.1, so we can see how does changing that error tolerancing affect the depth of your circuit. Perfect. Now I'll do it with you guys. Loss of fidelity. Let's go into synthesis. I'm going to go ahead and scrap all that. Oh, that's not where that goes. There we go. Okay, so 0, 0.5, 0.15, 0.3, 0.3, 0.15, 0.05. The only reason this should give you an error is if the values don't add up to 1. So you got to make sure your probability mass function adds up to 1. We only need 3 qubits here, and KL we want instead, what was that? Loss of fidelity. I believe I said 0.01 and 0.1. Cool. All right, so let's go ahead and keep analyzing this. Perfect. I'm going to go ahead and click synthesize. tiny qubits. So we need 3 qubits for this one. Perfect. And I'm going to go ahead and name this, 001. Going to go back and I'm just going to take one off there. Run it one more time. Boom. And I'm going to name this 01. Wunderbar. Okay, so let's take a look at the 2 circuits. This one requires 3 qubits. Very small, right? Depth of 9. Awesome. With the 3 8 single rotation gates, 4 C0 gates. When you tighten up that tolerancing by an order of magnitude, you end up with a much deeper circuit. 96, still 3 qubits, right? Number of qubits didn't change because you still have the same number of states you're trying to load in, but you end up with many more single rotation gates and C0 gates. So the tighter your tolerancing, the deeper your circuit's going to get. But if you execute both of them, you're going to see that they do match up much more nicely, the tighter tolerancing. And speaking of, let's go ahead and let's run that 0.01 on IonQ's Aria with 1024 shots, just to change some parameters up. So let's go back to 0.01, right? We're going to go to execution, right? Circuit 0.01. Perfect. Let's choose, right? We want to make sure we're going hardware, Aria. Perfect. It's a very long queue time, but hopefully you'll see results later. 1024. Let's call this job error 001 and click run. Oh no, it's very sad. I think it doesn't like that 1 week wait time. Yeah, 1 week, 1 day, 15 hours, 32 minutes. Okay, so the queue time's a bit long for Aria right now. But instead of that, let's go ahead and run on a simulator just so we can get some results. So let's see, IonQ simulator. Boom, boom, 3 seconds. Let's do 1024 again. Job name. Error 001. Yep, we're still on the 001 circuit. Perfect. Oh, let's run that. Beautiful. Very nicely matching what we're hoping to see. Now, if we do this, we go back to execution. We change that up and we say 01. All right, we can go ahead and do that. 1024, job name. Let's call this error 01. Run. Let's see that result. Not so close. Right, we should be seeing a nice kind of a curve here, and it just kind of chunked it out instead. Right, that's what happens when you have a circuit depth of 9. Very short circuit, lovely, but doesn't actually map your probabilities as closely as you were hoping. Awesome. All right. Yep. All right. Any questions so far? All right. So next thing we're going to do, we're going to be doing some things on the Python SDK. So you saw generally how you go ahead and use the IDE. There's more advanced things, of course, you can do modeling on that, but just wanted to give you a flavor of how you navigate through the different sections. Next, I'm going to show you how to use the Python SDK. So when you're in that onboarding section, it shows you this, right? Pip install, update Classiq. We always put the U just in case somebody already has Classiq and they just need it updated. But let's go ahead and install that. And we're going to be doing some arithmetic. We're going to be doing addition of quantum states. Perfect. And as I wait for people to go ahead and do that pip install, I just want to show that I think I was talking to some people in my booth earlier today. A fun thing I like to do in some of my longer workshops is to show how to use a grower's algorithm to solve out for a secret Santa. So this is the names of us in marketing at Classiq, Erik, Hannah, and Simon. And so it's essentially just another constraint satisfaction problem. And a constraint satisfaction problem like this can be solved using Grover's algorithm, using XOR arguments, right? So Erik can give a gift to Hannah or Simon, but not both, right? Erik can give, right, and so on. Hannah can give a gift to Erik or Simon, but not both. They all have a qubit register size of 1, right? Because it's either yes or no. There's not really more to do with that. And with those as all your constraints, those are the constraints you give to the Oracle. Thankfully, with the Classiq platform, you don't have to figure out how to build the Oracle. You just need to give it the constraints that are going to live in it. And then you go ahead and say, please run it for me, right? So we wire it together. We say, synthesize that model, execute it, print those results for me. And you can go ahead and see who's given who gifts. Perfect. All right, so let's see. Anybody still trying to install Classiq on their Python? This one sometimes takes people a little bit longer depending on, right, if you're using Anaconda and they need to update that, if you're using, certain versions of Python that need upgrading or whatnot. So all right, well, for the sake of time, since it looks like I have about 10 more minutes here, I don't want to waste anyone's time with that. Let's go and do the adder circuit. So in this one, we're going to add these two Euler states together, right? So we have these two states. We have state 1 and state 4. And essentially, we're assigning them values, right? We're assigning bit values to the quantum state. In this case, it would be 0, 1, and 1, 0 are the two states we're putting in here. Sorry, wrong way. It's 1, 0, 0, and 0, 0, 1 are the two states, and in bit notation, that's 1 and 4. And the same thing, we're adding 0, 1, and 5, 0, 0, 0, 1, 0, 0, and 1, 0, 1. And we at Classiq like to name them backwards because that's the ket from the bra, so that's why it looks swapped. So we're essentially adding 1 and 4 to 0, 1, and 5. And just as a quick sanity check, it's always important to figure out what should you be expecting to see as an output, right? So if we're adding 3 states to 2 states, how many outputs should we see? How many histogram bars?
Well, like adding them pairwise, like it's like 6.
Yep, we should see 6 histogram bars. If we see more than that, there's an error somewhere, right? Could be just due to the quantum computer or other things, but we should see 6 solutions, right? And importantly, the way we're distributing this, we have a 50% probability on states 1 and 4. We have, looks like 25% probability on states 0 and 1, but a 50% on 5. So whatever is added with 5 should be the highest 2 bars. So we should see 6 bars, but 2 of those bars should be higher than the rest. So it's always good to see, from this addition I'm trying to do, what should I be seeing at the end of the day? Perfect. So, so we want to go ahead and do this. We want to optimize it for the IonQ Harmony machine. We're going to go ahead and synthesize the model, optimizing for depth. And then we're going to see what are the resources needed from this, right? Once we go ahead and synthesize this. After that, we're going to go ahead and run it on Rigetti's M3 with 4,096 shots, compare those results, and then run it on the simulator. With about 8 minutes left, though, I don't think we're going to be able to code all that by hand. But hopefully this could be a fun homework problem for you afterwards. And if you have any trouble with it, you can always go ahead and message me on Slack, and we can talk about it too. But I do also want to leave room for questions if anybody has them. So definitely join the Slack community channel. That's where you can communicate with me, with our developers directly. A lot of times a lot of times university students have homework using our platform because some universities are using it. And it's always fun to see like 6 questions get asked, and it's all the same question within like an hour. And it's like, wait, okay, homework's due, isn't it? Like tomorrow. Cool. Let me help you out. And when you just see that influx, you know that something homework related is happening. So yeah, you can communicate with us at Classiq through the Slack community channel. And just for some fun, I'll open up to some questions, but I'll go into my Python file and show you some of the fun things I was doing at Classiq earlier, just to kind of see some of the breadth of the system. There's my secret 10 I was doing. But yeah, I was doing some state preparations, right? This would be some of the things we'd be going through, changing some loss of fidelity. And programming in Python is pretty simple, right? You define out the probabilities you want to do. You say, what is the object that you're calling? The object you're calling is state preparation. You have to define the model, which is what everything gets wired in. You wire it in. And in this case, since we're just doing a state preparation, we say model.state, synthesize it. So model.synthesize, and then show me the output. And we called the circuit, we called the, our circuit and circuit.showInteractive. And actually, when you do show interactive, it brings you back into the IDE to interactively visualize your quantum circuit. Yep, and here's the arithmetic. And again, right, you load in 2 probabilities. You define out the state preparations with these probabilities. You call your adder. And in Python, we just say we have a left and a right argument. Essentially, what are you wiring into that adder? Each with qubit register of 3. We wire in the state preparations, and then we say, for the adder, the inputs are the outputs of your 2 states. And then model it together, synthesize it for me. And yeah, here's the fun Grover's algorithm. So yeah, there's a lot of fun things you can do in the Classiq platform, different ways to visualize it, right? That the hardware comparison table, different ways to see your circuit connectivity maps, distribution. So I was just messing around with some data and seeing how can I optimize my quantum circuits? What should I run them on? I was doing a European call option too for some finance calculations, just seeing what would be my return on investment should I buy a stock at a certain price within a certain amount of time. So there's some pretty cool things you can do in the Classiq platform, and with very low coding altogether. Right? I was able to perform that European call option with this amount of code. And that's just fun to say. So yes, any questions, anyone?
Is there a way to, like, if you create a new model on this platform, to publish it, or
Absolutely.
within the platform?
Yep. So if you're planning to publish, we've worked with professors where we've given them, that little bit of language you put like at the end of your paper. But yeah, absolutely, you can publish with any of the models you develop on the platform, and any of the models you develop on the platform are only visible to you, right? There's ways to add in your own custom functions for the system to even optimize around as well. But again, only you will see that. Other users do not have access to any custom functions or algorithms that you develop in the system. Yeah, and that's pretty important because there's some fun projects professors are doing by, like, they're building their own hypothetical computers, because you can optimize quantum circuits by specifying the quantum hardware you want to run on, but you can also specify hypothetical quantum computers with hypothetical, circuit connectivity maps with gate sets that might not actually exist today, things like that.
Yeah, I've seen similar with classical computers.
Mm-hmm. Yeah, Andris, you had a question?
Yeah, I do. I was wondering if you can show us an example of, say, variational algorithm, and how much different it will look from like those Qiskit packages.
Yeah, this is a great time. Let's start from the Classiq platform here. I'm going to go into user guide. Let's do VQE. Let's see, it does take me, yep, VQE, I'll solve a result. Where is the VQE section? Variational quantum eigensolver. Perfect. All right. So you can go into that section and go ahead and see how to implement that. So you define out your molecule and generate the Hamiltonian. You define your ansatz, and then you optimize its parameters. So it takes you through all the sections here. Here's an example just doing that with H2. I've had some fun doing it for like LIH. H2O will take like a couple of minutes to generate because it's a bigger, molecule. But yep, so you can see how do you generate your ansatz, how do you define it. You can have as your output just the polystring. If you want to stop there, you can load in that polystring and continue. So you can develop your Hartree-Fock state, your unitary couple cluster. Yeah. You can even take it all the way up to seeing what your convergence of energy is and see that graph.
That's good. Thank you.
Absolutely. Oh yeah, here it is. Another section just developing ansatz for other applications and showing you some of the things you can toggle. Yeah, defining 1 and 2 qubit gates. Cool. Any other questions? Happy to answer. And again, right, the platform's free, so feel free to use it for your own purposes to play with quantum computers, even if you just want to use, Righetti's 80 qubit quantum circuits. If there's an upcoming quantum competition that you want to use it for, absolutely, free game, have fun.
Can I ask a quick question?
Yeah.
Does Classiq is there optimized like noise aware compilation if you have some sort of characterization, like perhaps like one, if you're thinking about like superconducting circuits, perhaps like one like coupler has more noise on it. If you've done some sort of tomography experiment, is there a way to include that and optimize the circuit for the error rates?
I have 2 answers for that. So first answer is we're aware of the we're aware of the fidelity of the different qubits for the different hardware. And if the hardware allows us to, we'll cherry pick which qubits to use. Not every hardware vendor lets you cherry pick which qubits to use. But the ones that do, we will, and try and use the higher fidelity qubits. But we're also partnered with Q-Control, who will handle a lot of the error mitigation process as well. And that's just a call in Python where you can go ahead and just say, yep, let's tie Q-Control into this and let's make sure that we run this with as little error as possible.
Okay, that makes sense. So this is more like the algorithmic step.
Yep.
And then interfacing with the hardware is sort of kind of slightly separate.
Exactly. I mean, that's actually why the partnership with us and Q-Control makes so much sense, because they start at that touching the hardware step and optimization. Cool, great question. All right. Well, it sounds like there's no more questions, but if you would like to message me offline, feel free. You can do so in the Slack community channel, or you can email me at eric@classiq.io. All right. Well, it was a pleasure, everybody.
Thank you so much.
Thank you so much.